start. So I wholeheartedly welcome everyone on this wonderful day. Really very happy to welcome you all to this 100th webinar of webinar series on spintronics. Good morning, good afternoon, good evening to friends wherever you are. I'm absolutely delighted to welcome the guest of this event, Professor Sudhakar Ponda, the director of NICER, Professor Vedanta Mohanty, senior professor and always a well-wisher of this event, from Department of Physics, NICER, and the chief guest and the speaker of this event is Professor Stuart S P Parkin, who will give a lecture in about 10 to 15 minutes from now. So, on behalf of my W2S team, co-convener Dr. Brajbhushan Singh, and NICER in general, I welcome you all to this event where we are celebrating for first 10 to 15 minutes about the successful organization of 100 webinars of this webinar series on spintronics, which we call as W2S. So, first, I like to give a very kind introduction to our guests of today's event. So, the first guest is Professor Sudhakar Ponda, Director of NICER. He is a string theorist, an associate to the Department of Physics at NICER. He is a fellow of all academies in NICER, in India, and he is a recipient of several awards like the Sibos Fellowship, Erskine Fellowship from USP, Canterbury from New Zealand, and recently he got the Biju Patnaik Award for Scientific Excellence. And he is always very kind and helpful for this event. So I thank you, sir, for being there with us. Then the next guest is Professor Vedanta Mohanty from Department of Physics. He is an experimental high energy physicist and professor at School of Physical Sciences at NICER. He has also been awarded several distinguished recognitions like in Young Scientist Medal, Santi Swarup Bhatnagar, Fellows of all academies, J.C. Bose Fellowship, and one of the recent attraction was Infosys Prize. And he, I think he is the spokesperson for the India Star Allies collaboration. And I think from January 2023, he will be working as the deputy spokesperson for the Alice collaboration at SUN. He is also very helpful and very supportive for this event. I thank you, Professor Mohanty, for being there with us. Then the speaker, none other than Professor Stuart Parkin, whom I think we don't need to introduce because he's so well known, everybody knows, but there may be some general audience, young students from NICER. So I would like to say a few words. Yeah, I will read actually later his full CV, but he is really one of the frontier person in the field of spintronics magnetism, and he is, he has got many such awards like American Physical Society, International New Materials Prize, Europhysics Prize, Innovator of the Year by R&D Magazine, Von Hippel Prize, Swan Medal, Penn Medal, and so on. And he will be giving a fantastic lecture. I know he gives wonderful lecture. Everybody enjoys that, and that will start in about 10 minutes. I like to nevertheless say a few words about the W2S activities, which we started during the lockdown, during the COVID period, remembering the painful times. But during that time, the idea was to somehow connect to each other and to hear and interact. And the webinar was one of the best platforms, best ways to communicate with each other, to stay connected from different parts of the globe. And we started that activity on 4th of June 2020. And later on, we organized almost weekly webinars. And we had got an overwhelming response for the registration. About 700 candidates across 25 countries have registered. And many times we have several hundred participants in different webinars. I am really thankful to those participants. For them, we could, get more energy to organize such webinars. And also, I'm grateful to many speakers whom I will just show quickly the photos of the speakers in the next slides. But I like to say also we have about 100 speakers now from about 20 countries. And that's a really nice thing. And I'm really, really thankful to all of them for their generous or their generosity to join this webinar series. Very nice thing was the W2S actually, when I was looking at the statistics, we had a wonderful combination of theory and experimental colleagues giving talks of different interesting areas of spintronics. And we also had many eminent female speakers. So that is another important part, like women in science. And we have actually several eminent female speakers in this platform. And we have covered almost all topics of spintronics, and I will show that. So this is the kind of global map. These are the countries from which we had the speakers, and of course several speakers from different countries gave talks, and now we are standing at the 100th webinar. So these are the speakers number 1 to 25 who gave beautiful lectures almost in 2020, I would say, maybe a little bit in 2021. This is speaker number 26 to 49. Again, you see known faces in the area of spintronics who are giving wonderful lecture. And the 50th webinar was very special, like today. So we were very delighted to have Professor Albert Furt, who was very kind to give the 50th lecture. And it was a really nice lecture, which calls 2D magnets from fundamental to spintronic devices. And after that, we continued the activity. So these are the speakers 51 to 74. Again, you see several distinguished scientists in the field of spintronics coming all around the globe, and they gave wonderful lectures. And this is the list of speakers from 75 to 99. Again, spanning from different areas of spintronics, from different places around the globe. And today, as we stand, we are celebrating the 100th webinar, and it is given by Professor Stuart Parkin. And this is really a great pleasure for all of us to hear him. And he will give it a talk about beyond charge currents, spin and ion currents for future data storage and computing technologies. So thank you, Stuart, for joining, and thank you all for joining. And on this occasion, I also kind of, these are the female speakers of W2S, you see also from different countries. And these are the topics which we have covered: spin caloritronics, magnetism, magnetic thin films, antiferromagnetic spintronics, spin pumping, neuromorphic computing, skyrmions, topological spintronics, organic spintronics, spin orbitronics, oxide spintronics, and so on. And the numbers in bracket are basically the talks we had in that particular area. So I like to sincerely thank, apart from the convener, co-convener, I'm really thankful to the team of volunteers who are really behind the scene, and a fantastic set of PhDs, and I think only postdoc is Dr. Anupama Swami. So they have done a wonderful job, and I like to acknowledge the efforts by Pushpendra Gupta, who is actually my driving force, who coordinated with the speakers to get the abstracts and so on, and many others, Hakti, who uploaded the talks, Kiti, Soyang, Ajay, they prepared the mementos, and other people who helped in different ways. Jorgit Sahu was a colleague working in the computer center who helped us to maintain the website. Now he has moved to a new job, but I acknowledge his great support. So with this, short introduction about the activities of W2S, I'm again, extremely happy, emotional to say that we could go up to 100th webinar, and I don't know what is next, but definitely we will try to see what can be done the best. But the good thing is we have heard excellent talks, and we have learned many things, and it was an excellent platform to exchange ideas. So with this brief note, I would like to now stop myself, and I would request Professor Sudhakar Panda, Director NICER, to say few words. So Professor Panda, please say a few words. Thank you.
Thank you, Subhankar, and good afternoon, good morning, good evening to all the people who are logged in and wherever you are in the globe. I'm actually happy to be part of this 100th webinar in the webinar series on spintronics. It's actually wonderful to see so much enthusiasm among my colleagues at Niger, and participants from what we heard is about 25 countries, and the 100th lecture is today. As director of Niger, I would like to extend my sincere thanks to the speakers for their presentations, the last 99 speakers. And today I extend my hearty gratitude to Professor Dr. Stuart S P Parkin, who has generously agreed to be with us today to give the 100th lecture in this webinar series. It will be a pleasure to hear you from your lecture. I like to congratulate Dr. Subhankar Vedant, a colleague of mine here in the School of Physical Science, for the excellent organization of this wonderful webinar series. As you saw, the notes he provided, almost all the topics on spintronics are covered, and there are many female speakers also are invited to speak. And this series would not have been possible without his effort and his team, of course. It appears that this is the only webinar series currently available in India focusing on spintronics. There are a few webinar series taking place in other countries. However, in future, we may be doing more of this type of online seminars as a way of interacting with one another scientifically, because this is what we have learned from the COVID, that you don't have to travel here and there. You can be comfortably sit in your office or in your drawing room, wherever you prefer, but we can still interact. Because in recent years, the spintronics has become one of the most active fields of research, and I'm very much pleased to share that my Niger colleagues are excelling in this research field. In past few years, Niger has produced a number of excellent articles in the field of spintronics, and I'm sure they will strive to continue that. And I wish all of you a great interaction. Hope this type of activity will spark new ideas, collaborations, or discussions. I hope in near future, whenever it is possible, you may be able to visit us in India, specifically in Niger, and see our beautiful campus. And with this, I thank you very much.
Yeah, thank you so much, sir, for your very kind words. So I would now request Professor Vedant Das Mohanty to say a few words.
Thank you, Professor Subhankar Vedant, and welcome all. Big thanks to Professor Stuart Parkin for agreeing to give this webinar. The topic that he will speak is not only the frontier area in science, but also something that colleagues and students at NICER are pursuing. In several talks at NICER in this area, I have seen the first slide invariably show your work, Professor Parkin, magnetic domain wall rest track memory published in Science. Always that paper comes up. I have read it, and thank you for educating me on this topic. I also take this opportunity to thank Professor Parkin for support to establish a Max Planck India partner group at NICER with Dr. Ajay Kumar Naik as its lead. I will echo which my director said, that hope you will visit us sometime at NICER. And at the end, let me congratulate Professor Subhankar Vedanta for so successfully organizing this webinar series on spintronics, bringing great speakers for discussions, which will further build up the spintronics community in India. Best wishes to him and his team. Thank you very much.
Thank you, Professor Mohanty, for your very kind and encouraging words. I would now request Professor Stuart Parkin to say a few words, not the talk, but just some words about this event. Please, Stuart.
Well, I'm very happy to be the 100th speaker, and I see you've had a fantastic series of speakers in this series of seminars, including Albert Verd, who gave the 50th talk. So I think I'm not sure there's much left to cover in the topic of spintronics after 100 seminars. But of course, I think it's wonderful that you have been able to attract so many wonderful speakers to talk about the exciting frontier of spintronic physics.
Okay, thank you so much, Professor Parkin, for these very kind and encouraging words. I would now request all of you to switch on your camera to take a quick group photo, if possible. and then we will almost go there for the talk.
Well, it's tough to do that.
So if you could switch on your video, that would be very nice. Okay, smile. It's wonderful to see nearly 200 people here and close to 100 in YouTube. So I think my team is taking snapshots. Please feel free to smile. Okay. I hope you guys have taken enough photos. All right. So I think it's time. You may kindly switch off your videos. Thank you. So I will again share my screen just to present some digital mementos. So yeah, I don't know. Okay. Okay, thank you. I like to just present some digital memento. Where is it? Yes. So this is a small memento from our W2S team to Professor Sudhakar Panda in recognition and appreciation for being a guest in the celebration of the 100th webinar of W2S. Thank you, Professor Panda. Then I would present the sharing my screen. And yeah, so I would just quickly read through Professor Stuart Parkin's little bit detailed biodata. Professor Stuart Parkin is the director of Max Planck Institute for Microstructure Physics in Halle in Germany and an Alexander von Humboldt professor at the Martin Luther University in Halle, Wittenberg. His research interests include spintronics materials and devices for advanced sensor, memory, and logic applications, oxide thin-metal structures, topological metals, exotic superconductors, and cognitive devices. Professor Parkin's discoveries in spintronics enabled a more than 10,000-fold increase in the storage capacity of magnetic disk drives. For his work that thereby enabled the big data world of today, Professor Parkin was awarded the Millennium Technology Award from the Technology Academy in Finland in 2014, and most recently the King Faisal Prize for Science 2021 for his research into 3 distinct classes of spintronic memories. Professor Parkin is an electorate fellow or member of the Royal Society in London, Royal Academy of Engineering, National Academy of Sciences, National Academy of Engineering, German National Academy of Science, Royal Society of Edinburgh, Indian Academy of Science, and the Third World Academy of Science. For the developing world, Parkin has received numerous awards, including the American Physical Society International Prize for New Materials 1994, Europhysics Prize for Outstanding Achievement in Solid-State Physics 1997, 2009 IUPAP Magnetism Prize and Nell Medal 2012 Von Hippel Award, Material Research Society, 2013 the Swan Medal from Institute of Physics London, Alexander von Humboldt Professorship International Award for Research in 2014. Then he got the European Research Society Advanced Grant at Sorbet in 2020. Professor Parkin has received 4 honorary doctorates. Professor Parkin has published nearly 700 papers and has more than 122 issued patents and has given more than 800 invited talks around the world. Professor Parkin was named as highly cited researcher by Claire Vette for the years 2018 to 2022 and has an H index of 126. So with this, introduction, I'm again absolutely delighted to have Professor Parkin with us, and I would now request him to give a talk. And during the talk, we will not take any questions. At the end of the talk, we will have the question answer session. So I would now request Professor Parkin to start his lecture. Thank you so much. You may kindly share.
Okay. Can you see my screen?
Not yet.
Oh.
Yes, it's coming.
Okay.
Yeah, we see it.
Okay. So, first of all, I'd like to thank the chairman and the organizers for inviting me to give this talk, the 100th seminar of this very exciting series of talks in spintronics. And as I just mentioned, I think all subjects have been covered. So I was asked to give a very general talk, and that's what I'm going to do. I'm not really going to talk so much about our mole research. However, in this movie, you can see some of the capabilities that I've built with my team since I came here to the Max Planck Institute of Microstructure 5 years ago. And here you can see a very state-of-the-art system where we connect an ultra-high vacuum tube, which is 15 meters long, to a variety of thin film deposition systems. So we can explore a variety of materials made by different techniques, pulsed laser deposition, the university, which is a very old university, one of the oldest in the world, and with whom we have a lot of collaborations. And I just wanted to make the point that you have positions available for PhD students and postdocs, junior group leaders, and even a directorship position in theory, if any of you might be interested. And some of the topics that I'm interested in include fundamentally atomically engineering interfaces for spintronics, for what we call COD, which has a source size of 15 nanometers, which is several times better than any commercially available machine. We're exploring new types of interfaces for superconductivity, and recently we've discovered a new effect, a Josephson diode effect, with which we hope to be able to generate triplet supercurrents that carry spin angular momentum for the purposes of building a cryogenic racetrack. And I was just fortunate to have received another ERC advanced grant, Supermint, that which we plan to use this to study this phenomenon. And then, of course, we're certainly interested in topology. Here I wanted to mention the reason why I came to Germany was I married this wonderful scientist, Claudia Felser. She's an expert in topological materials and has carried out an amazing series of discoveries over the last few years. These are just some members of my department. 5 years old. These are students and postdocs and scientists who've contributed to building all of these new capabilities which have been established just in the last 5 years. So I wanted to also say a few words about the Max Planck Society. Maybe you're not familiar with it. The Max Planck Society is a society that is funded largely by the federal government of Germany. It has 84 institutes, most of which are in Germany. They're shown here. And it has about 20,000 members or employees altogether. And the mission of this society is really to carry out world-leading fundamental research. And in my own institute, that's what we want to do. We want to carry out cutting-edge discovery at the frontiers of science, but also with a view to long-term technological impact. And so since I've joined this institute, we've essentially changed its focus to really atomically engineered materials and their impact on a variety of technologies in maybe 10 or 20 years' time. So back to the title of my talk, and of course you're all very familiar with the fact that charged-based computing devices have been tremendously successful, and over the past 40 years these devices have been based on the field effect transistor, on complementary metal oxide silicon technology, and the technology has evolved over 40 years by scaling the size of a transistor to smaller and smaller dimensions, and the size today is just a few nanometers. And because of that, the physics has changed and it's no longer possible to scale in the way that it was before. So we have to imagine new ways of building devices. And of course, you're very familiar probably with quantum computing. There are major efforts to go from essentially what is a digital computing infrastructure, memory, logic today, to quantum computing, which is really an analog. computing device where you take advantage of the phase of a wave function, and then one bit can have multiple billions of states. Now, this is very interesting, and spintronics can play a very important role here. A spin qubit is essentially what a ultra-scaled FinFET transistor is in a limit where you have only a tiny number of electrons. So this, it turns out, the spintronic-based or spin-based quantum computing is a very exciting area of research that I think has a great deal of potential. At the same time, and I'm not going to talk about this, another interest of many of us is this concept of what you might call cognitive computing. And then the concept is, we all know that the brain is an amazing device that thinks very energy efficiently. A typical brain uses 20 watts, and a typical supercomputer would use maybe 10 megawatts. So the difference in the power to carry out certain type of computations is 1,000,000 times. So there's a great deal of interest in, can we emulate the biological world in the, if you like, the inorganic world by building devices with principles that we've taken from the biological world. I think this area of research is in its infancy, and I'm going to maybe if there's time, make a few comments at the end of my talk about this. It's something that we're certainly working on. I think what then is my really talk here, I just want to make a few comments about going beyond charge and using spins. And at the same time, the biological world is devoted to using ionic currents. And I think this is something we're working on, and it's super interesting. By adding or removing ions as oxygen from an oxide, you can change it from being an insulator to a metal, and you can create a wide variety of super interesting devices. And finally, I think a very important concept is we actually go from the two-dimensional concepts that we use today fundamentally to three-dimensional devices. And again, this is why I proposed Racetrack 20 years ago, because it's fundamentally a three-dimensional device. But today, there's a great deal of interest in building three-dimensional devices, and even a FinFET today is a three-dimensional charge-based device. So again, as a very general introduction, then we could go back more than 500 years to the time in Germany of Johannes Gutenberg in the city of Mainz, which is a very beautiful city. And prior to his invention, then you had to basically write a book with a pen on a piece of paper or parchment. And he invented a technique for printing these books, and this really was enlightenment where knowledge could now be passed more easily between people. Before that, it was really confined to tiny numbers of people who had access to these super expensive books. So this was the world of analog, an analog world that began 500 years ago. And you can really say it lasted 500 years until about 50 years ago. Then the world of digital data became possible. And this was with the invention of the magnetic disk drive. Shown here is a modern disk drive, but 40 years ago or 50 years ago, these disk drives would hold just a few thousand or a few tens of thousands of bits, and they would be giant machines the size of a refrigerator. And over the last 50 years, the capacity of a magnetic disk drive has increased 1 billion times. And we like to think that the last 4 orders of magnitude was because of a spintronic device that I invented when I was at IBM. I'm going to briefly discuss that device in a moment. On the left-hand side, and you can see this device, you can see a magnetic force microscopy image of magnetic bits as they are shrunk in size. And really, we like to think today, and this is certainly the case, that all the major corporations today are based on the concept of storing digital data and vast quantities of this digital data, accessing it, and then you can take advantage of this data in ways that wasn't possible before. So, for example, Google is one of the leading companies in the world in artificial intelligence, and they do that using neural nets that were invented 30 years ago. But today, the same ideas, because of the explosion of data, now become possible to use artificial intelligence because of that data and carry out amazing concepts that were not possible before. And then in the cloud, what would you see? You basically see massive numbers of these magnetic disk drives. And today, about 70% of all digital data is still stored in magnetic disk drives. The rest is stored in a variety of devices, including solid-state drives, which are basically based on flash memory, which is a charge-based memory device, which we want to change to racetrack memory. So then, if you then look, this is a paper, now it's 7 years old or 10 years old, and so it's a little bit out of date, but basically this paper in Science showed how the storage capacity and where data was stored in the world changed from analog, basically old-fashioned books, newspapers, it changed to basically magnetic disk drives. And this happened in about a decade. And so basically a decade ago, that was when most data was transformed into digital data. And because it's accessible in the cloud, everybody has access to this digital data. And that basically, if you like, is the second age of enlightenment, where every individual can access basically all the knowledge in the world through digital libraries in the cloud. So now we go to spintronics, and again, going to give a very general introduction. And so spintronics says, well, the electron has a charge, and we can flow currents of electrons and manipulate those currents and therefore build transistor devices. We can store electrons in a capacitor and build a memory device, but the electron has a spin, and it's a quantum mechanical property, therefore it takes two values, spin points up or its spin points down. And then it turns out then we can create spin currents in a very simple way. First of all, if we take something like copper, copper has equal numbers of spin up and spin down electrons, and when current flows through this material, the current is carried equally by these two types of spin polarized electrons. But it was known in the 1930s that if you pass current from, let's say, a battery where it's unpolarized into a magnetic metal whose magnetization points in a given direction, then the current quickly becomes carried predominantly by one type of spin polarized electron. And this was a concept that Neville Mott originally introduced. So the concept is that just by passing a current into a ferromagnetic metal, because of broken symmetry, then because of the magnetization, then the electrons are scattered at different rates. So the mean free path for spin up and spin down electrons is distinct, and the current is carried by electrons of one spin type. So now you can create what we called a spin valve. So a spin valve is shown here. You have two magnetic layers. The lower electrode shown in blue, the magnetization points to the right. The upper electrode magnetic layer shown in red points to the left. And in between, we have a copper layer. So now what happens when these two layers are aligned anti-parallel to one another, as shown here, then electrons in the blue layer are carried by, let's say, the blue electrons pointing up, and in the red layer, they're carried by the red electrons pointing down. But because if the copper layer is sufficiently thin, the electrons can pass from one layer to the other. And so if they pass from the blue layer into the red layer, they will be scattered and vice versa. So in this case, all the electrons will be scattered in one more strongly than in the case when these two layers are aligned parallel to one another. And so this is what we called a spin valve. In this case, by reorienting the magnetic moments, you can change the resistance of the device. And the two magnetic layers are not coupled to one another. You just rely on an external magnetic field. This is what we call the spin valve sensor, and which we incorporated into magnetic disk drives. And this was actually in 2007. IBM introduced this spintronic sensing device into these into magnetic disk drives. And of course, the spin valve was the concept of the spin valve we came up with because of the original work by Peter Grunberg and Albert Fert, who discovered giant magnetoresistance in a set of iron chromium multilayers grown by molecular beam epitaxy at low temperatures. In those cases, the magnetic fields required to change the orientation of the iron layers, let's say in a superlattice, were very large. They're of the order of 2 Tesla. Here, we need fields of just a fraction of an Ørsted to reorient those magnetic layers. So this spin valve then is a very interesting device. It can detect tiny magnetic fields. Now, it turns out it's much more complicated than that simple cartoon, because we actually design the magnetic moment of one layer to be orthogonal to the magnetic moment of what we call the reference layer. And then, as in this cartoon, when the spin valve device is moved over the surface of a magnetic film in a magnetic disk drive, in which the data is encoded. You can see here in these, there are blue and red domains where the magnetization points up and down, and the boundaries between these regions give rise to some tiny magnetic fringing fields, and these are then detected by the spin valve, and the maximal sensitivity is when the two magnetic layers in the spin valve have their moments orthogonal to one another. So I'm again not going to say much more about spin valves. That's a technology then that's been used since 2007, and essentially it's used in all magnetic disk drives. Was used in all magnetic disk drives for about 10 years, and then the technology evolved from a spin valve to something that actually looks very similar. It used all the same, what I call spin engineering principles that actually I discovered and proposed to build these spin valves. We now use them in something called a magnetic tunneling junction. And I know these have been probably extensively discussed in the 100 seminars of this series. But just to remind you, a magnetic tunneling junction is essentially the same as a spin valve, except the copper layer is replaced with this gray layer, which is an insulating layer. And in 2004, I showed that, in fact, using magnesium oxide as that tunneling barrier, you could see changes in the resistance of a tunneling junction at room temperature of more than 200%. And this is 20 times that of a spin valve metallic system. And because it's an insulating layer, the resistance is much higher and you get much greater sensitivity. So since 2017, approximately, very rapidly, all the magnetic disk drives sensing devices now use this magnetic tunneling junction device. And again, the two magnetic layers would have their moments designed in quiescent state to be orthogonal to one another for maximum sensitivity. And then, so this was basically then has been used in disk drives for the last almost 5 to 10 years. And the magnetic tunneling junction then is a very interesting device because it's based on tunneling. That gray thin insulating layer can give rise to very large resistance values. So we proposed in 1995, which is 27 years ago, we could build a very interesting memory using magnetic tunnel junctions. And originally, we proposed that these would be switched by magnetic fields we would create by passing currents through bit and writing lines. And the bit lines and writing lines are shown in this cartoon. So basically, this device is very similar to many CMOS memories in that you have a so-called cross-point array. You have a series of parallel electrodes and another series of parallel conducting wires perpendicular to the first set. And at the intersection between a bit line and a write line, we place this magnetic tunnel junction, so the current flows perpendicularly from one line to the other, basically vertically through that structure. And we can basically change the resistance of the device so that it is optimally designed to be compatible with the input resistance of a transistor, an FET. And the transistor then is used to pass current through the device and to detect that current, how much it is. When the two magnetic moments are parallel to one another, as in the top, the current flows very easily. You get a big current. And when the moments are anti-parallel, then the resistance is much higher and the current is reduced. And this kind of magnetic tunneling junction device we propose could provide for a high performance memory, non-volatile memory, where the information is encoded into the direction of let's say the free or the memory layer of this tunnel junction. So the secret in building these devices is you have to avoid all magnetic stray fields. I'm going to come back to that later, but I invented something I called a synthetic antiferromagnet, and this is critically important to building both spin valves and magnetic tunnel junction sensors and memory elements. You have to eliminate all the stray fields from one of these layers. And you can do that by creating an artificial anti-ferromagnetic layer using an oscillatory long-range coupling that I found was common to nearly all the transition metals in the periodic table. And typically one uses an ultra-thin layer of ruthenium to create a very, very large anti-ferromagnetic coupling and a synthetic antiferromagnet. We'll come back to that briefly later. What I wanted to point out here then is that if you look at the top, I want to show you over time the discoveries we made in 1988 and 1991 enabled us to propose a spin valve sensing device, and it only took a few years, 6 years after I made these discoveries, the materials, the oscillatory interlayer coupling, the interfacial nature of the spin-dependent scattering that gives rise to giant magnetoresistance. All of these ideas, dusting layers, were used in the very first spin valve device in 1997. As mentioned, 10 years later, the devices switched to magnetic tunnel junctions, but essentially the same kind of structures. Now, we can see for the last several years, the magnetic disk drive technology is evolving very slowly, so slowly that there are only two major companies left that build magnetic disk drives, and both those companies then have decreased their research efforts because basically this is a technology that it's difficult to evolve beyond its current state. And basically it's limited by the size of these tiny magnetic regions in a magnetic film that can be written and can be detected. They can actually be detected. It's the writing that is the problem today, and the thermal stability of those regions. As you shrink the size of the magnetic regions, then the total net magnetic anisotropy becomes smaller, so you need to increase that anisotropy, and that means you need much higher writing fields. And there's a limitation to the size of the writing field that can be achieved in a disk drive. So I mentioned this MRAM, magnetic random access memory. It shows you here on the bottom. You can see actually a cartoon I made so many years ago, but basically this is the basic structure that's even used today. And the idea we proposed originally was in 1995 to use magnetic fields to write these magnetic tunnel junction elements. Then John Slonczewski proposed soon afterwards that we could use current itself passing through the tunnel junction or through a spin valve originally to switch the magnetic state, because the spin current carries spin angular momentum. Therefore, the current of electrons can be used to deliver angular momentum for writing a magnetic tunnel junction device. So it took us about 4 years, and this was a collaboration with Bill Gallagher, who was a scientist at IBM's laboratory in New York State. I was based in California, and together we built a 1,000-bit array of magnetic tunnel junctions in 1999 and demonstrated the basic principles of a magnetic random access memory. And later on in 2001, I discovered this super high tunneling magnetoresistance values in magnesium oxide-based tunnel junctions. Actually, IBM wouldn't let me publish that work for 3 years. And in 2005, we demonstrated the first field switchable 16 megabit CMOS-based MRAM. So it's a fantastic achievement in a relatively short period of time. And I just wanted to point out, without going through all the intermediate steps, that in 2019, Samsung was the first company to announce that you could buy from them in its foundries, you can buy a spin transfer torque embedded magnetic random access memory technology at the 28 nanometer CMOS node. And today, of course, the technology continues to evolve. However, there's still some limitations to MRAM. The limitations are mostly the current needed to write the device, which requires larger transistors than are available. And secondly, turns out a technical detail, it's the etching of the magnetic tunnel junction elements that has to be done physically rather than chemically that limits how closely they can be packed. These are the limitations today of MRAM. So this is what I basically discussed. This is our work, 1995, 1999, our first tunnel junction developed at IBM in 2005. And then I mentioned that these companies, many companies are developing MRAM over the last several years, and Samsung was the first one to have a technology you can buy from the company. Now, I wanted to point out, these are innately two-dimensional technologies in the sense that you have a single array of transistors in a CMOS technology, which are used to access and read these devices. This limits, of course, the eventual capacity of these technologies, because it's not possible to continue to scale in 2 dimensions the transistors. You need to do something else. And I want to then talk about this device. And again, this is a very old cartoon that I first prepared with the help of Kevin Rush many years ago. And this was my concept, that we would build a device that is innately 3-dimensional. Build tall, vertical, magnetic nanowires. And in these nanowires, we would magnetize the wires in these blue and red regions, magnetization pointing in opposite directions. And the information is encoded in the walls, the domain walls between red and blue regions. And my concept was that if you pass a current through this nanowire, which is homogeneous, all of these domain walls would move synchronously around the racetrack. And therefore, we could move the data to reading and writing devices. So this is a very interesting concept that I thought, because it's totally unlike any other memory technology at that time, which was 20 years ago, and even today. It's the only one in which you move the information around the memory device. And therefore, in one device, we can store 100 or hundreds of bits. And now, so when I proposed this, people were very skeptical, but it took us about 6 years before we actually demonstrated the basic principle. And this was a paper in Science. Actually, it has nearly 5,000 citations today. So how does it work? And then again, going back in time, this is actually a cartoon from Sademichi Maekawa from some time ago. And it basically, the essential principle is that of the Mott concept, that if you pass a current into a magnetic material, the current is spin polarized. And then the angular momentum of the conduction electrons, as shown in this cartoon, can be transferred from the conduction electron to a magnetic moment in the domain wall. And approximately 1 electron per magnetic moment is needed to rotate that magnetic moment. Therefore, if we have a big enough current, we can rotate sufficient numbers of moments that the domain will move. And in principle, because here you can see the polarization of the electron current is determined by the local magnetization, this should mean all the domain walls will move in the same direction. And that's what we showed initially in some very soft nickel and cobalt-based materials, in which we knew from really the decades of work prior to this, to working on this, that it was known that nickel and cobalt-based magnetic alloys can have very large polarization of the currents, up to 70%. Passing through those alloys. This is why originally I decided to look at these materials. However, I call this racetrack now memory 1.0 because the domain walls in soft materials can be very, very large. In fact, they're not well defined. They can expand if there's defects or for some other reason. They can become microns long, even though they might be initially a few hundred nanometers in size. So this doesn't work technologically, although we did demonstrate the motion under current of a series of domain walls in the same direction. However, if you change to materials in which you have significant perpendicular magnetic anisotropy, now the size of the domain wall is governed by the ratio of exchange to this anisotropy. If the anisotropy is big enough, then the domain walls are very narrow. We estimate now the domain walls we currently are using in atomically engineered cobalt-nickel multilayers are of the order of 6 nanometers in width. And these domain walls then, again, if we pass current through a cobalt-nickel multilayer, will also move with current. And as you can see here, they move in the opposite direction to the current. And that's because the polarization of the current in these nickel and cobalt-based alloys is majority spin polarized. Now, what was a very interesting discovery a few years ago was that if you if you now create a structure, the same cobalt nickel multi-layered structure, and place that multi-layer on this yellow layer, which is a layer of platinum. Now, when you pass current through this system, then the current moves in the opposite direction and moves much faster. And the mechanism for moving these domain walls is something that we unraveled together with some other groups around about the same time. And we demonstrated it's because the platinum has a phenomenon called a spin Hall effect, that current passing through platinum will generate a spin polarized current flowing perpendicular to the charge current. And this spin current then can flow into the racetrack and apply torques on the domain walls. And then they will move, and they will move very efficiently. So I mentioned in my previous part of my talk that just as for spin valves and for magnetic tunnel junctions, the magnetic moments, magnetic regions give rise to large stray fields. This is shown in this cartoon. These stray fields cause interactions between the domains in a single racetrack and between one racetrack and another racetrack. You have to eliminate them. And so I had originally proposed for a spin valve, it was the same problem, that the two layers in a spin valve are strongly coupled by dipole fields. And in fact, they'll either be parallel if the moments are on top of each other, or if you have two moments on the side, they'll be antiparallel. Anyway, so it means that if they're in plane magnetized, they'll be antiparallel. If they're perpendicularly magnetized, they'll be parallel oriented in two layers. You have to eliminate these dipole fields, which increase inversely with the size of the device. So we did that by this invention of mine of a synthetic antiferromagnet. And in the racetrack, we did the same thing. We made two identical racetracks, one on top of each other, coupled through an ultra-thin layer of ruthenium, although recently we've discovered a new family of materials which give rise to oscillatory interlayer coupling. These are L10 compounds, in particular ruthenium aluminum. And this ruthenium aluminum is very interesting because it enables us to build the racetracks from other types of materials. But here, this is a racetrack with an ultra-thin ruthenium layer. It's about 7 angstroms thick, and this causes anti-ferromagnetic coupling between the racetrack above and below. So as you see in this cartoon, here we have some red and blue domains, and underneath they have blue and red. And this is because of this anti-ferromagnetic coupling. So it turns out what is also very important in this racetrack memory is that these domain walls, in order that the spin Hall effect derived torques, these are called spin orbit torques, from this platinum layer, then these walls have to be chiral. Otherwise, they don't all move in the same direction. They have to be anti-clockwise, or they all have to be clockwise. I want to briefly discuss that in a moment, but just again to remind you, these are innately three-dimensional technology, and this is very important. Now in the same space where we would have one electron or one, where we would have in a tunnel junction, 1 bit, we would now have 100 bits. So we can increase the capacity compared to conventional MRAM by 100 times. And this is why it's so exciting. And that's why I think it's very exciting. So this is the type of work that we do, shown here. Until recently, we were largely looking at racetracks, the horizontal, and we can detect the domains by optical means. We just shine a light onto a racetrack. The light is polarized in a planar direction, and the plane of polarization is rotated in clockwise or anti-clockwise, depending upon the direction of magnetization. On the right-hand side, you can see the type of structure here. This structure consists of these green and blue layers. The green layers are cobalt layers. They're 1.5 angstroms thick. The nickel layers, 7 angstroms thick. And the important point is these interfaces give rise to very strong perpendicular magnetic anisotropy. And then you can see underneath we have some orange or red layers which are formed from platinum or some other material which converts charge to spin very efficiently. And again, recently we published earlier this year some new materials, some 5D transition metal aluminum alloys, in particular iridium aluminum, where the spin Hall angle is more than 10 times larger than in platinum. And therefore, because the efficiency of generating spin currents from the charge current flowing through these new materials is so big, it means we could use currents to move domain walls, which are 10 times smaller for the same velocity. So it turns out when we went to the top material, there's just a racetrack consisting of cobalt, nickel, cobalt. To the bottom, this is the synthetic antiferromagnet. Now we have two cobalt, nickel, cobalt layers separated by this yellow layer of ruthenium. And as you can see in this cartoon, these layers are coupled anti-parallel to one another. Now, because of a small hiccup, the platinum layer actually itself becomes magnetic by proximity to this cobalt, nickel, cobalt layer. So we have to balance the cobalt, nickel, cobalt, the lower layer, plus platinum moment with the upper layer moment. If we do it properly, the two moments will be identical. And therefore, there's no net magnetization anywhere in this racetrack. We eliminate all dipole fields. And we also discovered in this paper we published in 2015 that the domain walls now move up to 10 times faster than in a single magnetic layer. We discovered a totally new type of spin orbit torque, which is derived from the strength of the antiferromagnetic coupling field through ruthenium. That magnetic field gives rise to a huge torque that's much more effective than the torques derived from the spin Hall effect. So this is very interesting. And now we can move these domain walls in these synthetic antiferromagnetic racetracks at speeds of more than 1 kilometer per second. Now, as an aside, I'm not going to say too much about three-dimensional racetracks, but working very hard to make these types of structures by a special technique, atomic layer deposition, so we can deposit the racetracks not horizontally, but on vertical walls. And we've recently, we believe we can now achieve that. And therefore, we now have a means of making vertical three-dimensional and build the devices that I proposed more than 20 years ago. So again, I think we're running out of time, unfortunately. So unfortunately, I won't be able to say much more about these ingredients that make racetrack memory possible. But it turns out it's all to do with engineering multi-layers on the atomic scale, where the individual layers are just one to a few atomic layers thick, which is very interesting. And at the same time, it makes it very difficult to predict the properties of these materials. So it's easy today to predict, let's say, a topological material. You can calculate the electronic band structure and then look at all the properties of multifermions, Dirac and Weil types of nodes, and calculate the properties in a band structure. However, the interface is very difficult to calculate, even the structure of an interface and its properties. So this is why it's very intuitive as to how to build structures in this way. Nevertheless, we've made huge progress in, and others, in developing very interesting atomically engineered multi-layer structures for spintronic applications. And some of the most important ingredients are shown here. The anisotropies that can be induced by interfaces, something I didn't discuss, but typically it's an interface with a heavy metal layer like platinum, palladium, tungsten. You get something called a Delezinski-Maria interaction that causes the magnetic moments above, in the layer above, to want to be perpendicularly oriented in a chiral manner. This is a very interesting point, and this means in this cartoon, you can see the red moment pointing up, and then the blue moment pointing down. Then we form what's called a nail wall, shown by the green arrow, where the magnetization in the domain wall, as it rotates from up to down, points perpendicular to the wall. And the very next domain wall do the same thing, but because it's clockwise, then the moment in the middle of the wall, shown as the green arrow, will be pointing in the opposite direction. The chirality is preserved. Now we can change the chirality by changing the nature of that underlayer from platinum to tungsten, or by putting the platinum layer on top rather than underneath. Then it would change the chirality. I mentioned already that these layers proximity-induced magnetization is very important, and recently we have some very exciting results published in Nature Materials, where we demonstrated not only can we make platinum magnetic by proximity to a actually we used in that case YIG, which is a soft magnetic, ferrimagnetic insulating garnet, but we also demonstrated we can make platinum superconducting by proximity to a superconductor, a conventional superconductor like niobium, and we demonstrated for the first time a Josephson diode effect through platinum when it is magnetized by proximity to YIG. If we switch the direction of the magnetization, we switch the direction of this so-called Josephson diode effect. That means supercurrent flowing through platinum has a density, a critical density beyond which it is no longer superconducting, which is different when the current flows from a left to a right niobium electrode placed above the platinum than when it flows in the opposite direction. So this is very exciting. We're doing a great deal of work on proximity-induced superconductivity to create triplet supercurrents that could carry spin angular momentum and therefore enable us to manipulate magnetization at cryogenic temperatures without the use of any energy. We think this is very exciting, and this is something we're working on. I mentioned spin Hall effect, and this work is now published in Advanced Materials. We've seen spin Hall angles now exceeding 1, which is, as I said, several times larger than in platinum and in conventional materials. We think this is very exciting work, and it uses 5D transition metals and aluminum, and now with other materials, and it's related to extrinsic scattering. It's not an intrinsic effect, so it's also very difficult to calculate theoretically. Finally, synthetic antiferromagnets, I already talked about, are super important to build any type of magnetic device. Now, if there's time, I want to talk briefly about non-collinear spin textures. So what does that mean? That means going from chiral domain walls, we can actually make more complex textures. On the left-hand side, you see the typical Heisenberg exchange favors the nearest neighbor interaction between two magnetic moments to be ferromagnetic or antiferromagnetic, but I also mentioned this Dzyaloshinski-Maria interaction, which is found in compounds where typically you have strong spin-orbit coupling, or at interfaces, as I mentioned, with layers that are spin-orbit coupled. This leads to, as you can see from the top right, an energy that minimizes the energy when the moments are orthogonal to one another. This leads to, for example, spin spiral states, as shown at the bottom, where the magnetization then, by combining Heisenberg plus DMI, forms a spin spiral. And this can then lead to something called a skyrmion. This was discovered 10 years ago by Christian Fleider in Munich, here in Germany, where he showed the formation of these very interesting circular objects and arrays of these objects by neutron diffraction in a so-called chiral material, a B20 manganese silicon material. I don't want to talk about that. I want to briefly mention these other objects. So the idea is you take a material which is perpendicularly magnetized. If you have this chiral exchange interaction, you can form, for example, these 3 distinct types of skyrmions. The material, which otherwise would have a uniformly magnetized magnetization, under some regions of field and temperature will break up, so its state will consist of an array, typically hexagonal, of these circular objects. And the one that was discovered originally by Christian is this block skyrmion on the left. And if you look carefully, I hope you can see that when the magnetization outside this circle is pointing up, in the very middle of this circular object, it's pointing down. And if you go along a radius, you can see that the magnetization rotates in the plane perpendicular to the radius. That's a block skyrmion. On the right-hand side, you can see a nail skyrmion. In this case, the magnetization rotates from an up to a down direction along the radius, but by rotating in a plane parallel to the radius. This type of nail wall is exactly the same as in the racetrack that I was briefly discussing. And then finally, there's a very interesting another object called an anti-skyrmion. And if you look here, you can see as you rotate around the circumference, the wall changes between a nail and a block type, alternately around the circumference, and the chirality also changes. This anti-skyrmion was theoretically predicted, and we were the first to discover it. And in fact, this was work done by Ajaya Nayak, who's now a professor in your institute in NICER. And we did this by, when I came to Max Planck, I inherited a very old transmission electron microscope, and we modified it so we could carry out a technique called Lorentz microscopy. What does that mean? That means on the right-hand side, you can see we have a highly focused beam of energetic electrons, 300 kilovolt electrons, and we make then from a single crystalline material, these are materials made by Claudia Felser and her collaborators in Dresden, we make a very thin slice of this material from the single crystal, which is electron transparent. So this electron beam can pass through it, and we detect the beam on the other side of this specimen, and then because of Lorentz forces, the beam will be rotated. And in the case of a block scanmion, the beam, because of the nature of that domain wall I mentioned, the Lorentz forces cause the electron beam to be focused in the middle of the object, and you will see a bright white spot, as shown on the bottom left. And on the right-hand side, in a nail scanmion, it turns out because now the magnetic moments in the domain wall are oriented parallel to the radius, as shown in this cartoon, the Lorentz forces then are around the circumference, and basically there's no change in the nature of the electron beam. It's just the electrons are rotated. And finally, in the anti-scanmion, we calculated this is what we would expect to see. We don't see a single white blob as for a block scanmion. We don't see nothing as in nail. We would see this clover leaf, 4 blobs, 2 white blobs. That means the electron beam is deflected away from the object to the top and bottom, and 2 regions shown in black where the electron beam then is decreased in intensity. This is we can calculate by micromagnetic simulations and something called transport intensity equation, TIE. This is what we did, and then this is what we saw. And the top left, this is, you can see the first anti-scanmion seen by, directly imaged by Lorentz microscopy, and this we published in Nature 5 years ago. This is again work by Jai Nayak. And you can see on the top, on C, you can see an array of these anti-scanmions, an hexagonal array. And in the microscope, we can change the magnetic field and explore the phase stability, and we found that they were stable over a wide range of temperature. And I just wanted to point out then that we could also use magnetic force microscopy to detect these objects. This is shown here on the left side. You see these magnetic domains. We have a magnetic tip, and we detect the bending of that tip using a laser, and the stray fields from these domains cause the bending of the tip, and that's what we detect. I don't want to discuss this in detail, but this enabled us, for example, to see in the same material where we saw these anti-scanmions, then we see these spiral phases, helical phases, depending upon the temperature in the field. So basically, if we apply a big enough field, we will see a uniformly magnetized state. As we reduce the field, we'll see scanmions, anti-scanmions, and then we see this spiral state. And it turns out that the helical state in this system in which we see anti-scanmions, the direction of that helical state is only along one of 2 perpendicular crystallographic axes. And we can change the orientation of the helical spiral by applying in-plane magnetic fields. But what's most interesting here, and what we're showing is a magnetic force microscopy image of a lamella that which we've made by focused eye milling, in which the thickness varies, as you can see, from 0.6 microns on the left side to 4.2 microns on the right-hand side. And you can visually see from this magnetic microscopy image that the period of the helix changes from left to right as we increase the thickness. And this is summarized in G. The period of this helix is varying from 100 nanometers when the lamella is 600 nanometers thick, and more than 1 micron when the lamella is 4 microns thick. This is the first time in any of these scanmionic systems that such a strong dependence of the helical period was found with thickness. And now by changing the magnetic field, we can, increasing the perpendicular magnetic field, we switch from the helical state, where again, in the magnetic force microscope, I didn't say, we're looking at the out-of-plane component of magnetization. In the Lorentz images, we look at the in-plane component. Here we look at the out-of-plane component. And so basically, the out-of-plane component goes from up to down, and that's what we see in A. And then by increasing the field, we start to see these white blobs. These white blobs are the anti-scanmions, and we're looking at the magnetization pointing in the opposite direction in the interior of these skyrmionic objects. And you can clearly see that their diameter is increasing from left to right in this image as the thickness of this lamella is increasing from 0.6 to 4 microns. And on the right-hand side, you can see how the diameter changes from 100 nanometers to more than a micron. And then, of course, when they're micron-sized, we can just image these anti-skyrmions using optical techniques. So this is what makes these anti-skyrmions so interesting. Very complex magnetic texture, which is derived from the symmetry of the Dirizinski-Maria interaction, which is coupled to the symmetry of the crystal lattice. And this was the first observation. Now this has been seen in the same material. This is, by the way, a Heusler compound by Yoshi Tokura's group. They made exactly the same crystals that we had used, and they basically discovered the same result. And finally, I just wanted to mention one other effect. I think I probably have to stop then. I wanted to mention some very nice work by Jagannath Jena. He's another student in my group now, a postdoc, and he discovered in the same Heusler material that these anti-skyrmions can sometimes form these elliptical skyrmions you see here, and these are actually elliptical block skyrmions. And this was the first time that in one material you've seen two topological objects. The reason why people are excited by these skyrmions is that they're topological. There's a certain winding number associated with their magnetization that in principle increases their stability, let's say, with respect to temperature. And anyway, as a function of temperature and field, then Jagannath showed that we could change from these elliptical structures to the anti-skyrmion structures. And I think I have no time to discuss. You can read about it in this this paper in Science Advances. We also propose maybe we could use a combination of two topological objects to create a very interesting racetrack device. Well, we haven't yet demonstrated that, although on the left-hand side, you can see a real wire that we've made from a single crystal, and in which we can see the coexistence of anti-skyrmions and skyrmions. So this is certainly a possibility. Now, I think I'm running out of time. So I said at the beginning, I wanted to talk about ionic currents. I think I don't really have time to do that. But the idea is, as you all know, that more and more energy is being used to store all the massive amounts of digital data that we're creating. We need to do something else. And I don't have time to discuss this, but we have a very interesting set of programs here on can we build devices that more emulate the brain than a CMOS processor. And as you all know, the biggest problem with CMOS is that the memory and the processing devices are separated, and you basically have to continuously transfer data from the memory to the processors in order to carry out computations, and that takes a huge amount of power. Basically, the clock rate is the same, and today the CMOS devices use huge amounts of power when they do nothing, whereas our own brain, when it does nothing, it uses very little power, it's reconfigurable, most of us can learn, and it's fault tolerant, and it's highly parallel. So we want to build devices like that, but I think I don't have time to discuss it, but originally, a long time ago, I proposed we could use an array of tunnel junctions to emulate spike timing dependent plasticity. So the point is, in a brain, you have neurons. Each neuron is connected to each other by 10,000 wires, which are called synapses. And it's the strengthening and weakening of these synaptic connections is how you store information. And what's interesting is, again, unlike conventional memories, where one device stores one bit, in a brain, 10,000 connections stores a bit. So information is basically distributed, and that's very interesting. We are actually building devices similar to this, and you can do it you can build synapses and neurons using charge-based devices, using spin-based devices, and using ionic-based devices. And that's our efforts. We're doing both spin-based and ionic-based synaptic and neurons, but I don't have time to discuss. So therefore, coming to my conclusion, and just in my talk, I briefly mentioned we want to move from today's two-dimensional memory logic devices to innately three-dimensional devices. We can do that in racetrack memory. And we've made enormous progress since I proposed this 20 years ago. Today, we've demonstrated the basic principle. We can move domain walls at speeds of more than 1 kilometer per second. We can eliminate all the dipole fields. And we believe this racetrack memory, we're on track to enabling it to become the next spintronic memory after spin valves. and after tunnel junction-based MRAM, I think this is going to be a fantastic new memory that will be super fast, highly energy efficient, and super dense. And then I guess in the future, we hope that we can build cognitive devices, either using spin-based or ion-based, current-based devices. So I want to thank you so much for your attention. Sorry, I've taken more time than I should have. Thank you.
Oh, wonderful lecture. Thank you so much, Stuart. Excellent lecture. I'm sure everybody agrees that we all enjoyed. So it's now time for some question answers. I'm requesting you to raise either hands or you can write message in the chat box in case you want me to read it. Okay, we'll go with Akshat Misra, please. Oh, well, let me allow to unmute. Yeah, so you should be able to unmute and ask your question. Akshat, please.
Hello, Professor Parkin. It was a very nice talk. So I had a few questions about one of the last slides in which you mentioned that your group has tried using two different types of skyrmions for racetrack devices, like you created a wire. So how could you benefit from using two different type of skyrmions? Like you said that they are topologically different.
Yeah,
like how would you benefit using?
Yeah, you benefit because the concept is that they would, in principle, be more stable than, let's say, a chiral domain walls. In principle, chiral domain walls also have some degree of topological stability, but in principle, people argue that these topological objects should be more stable than otherwise. That's the main goal. But I agree with you, it's not so clear, because these topological objects typically are found over limited ranges of temperature and magnetic field, and they're also much more difficult to create. Nevertheless, it's very interesting conceptually.
Yeah, okay, so there is no solid motivation behind using
No,
like
there's a solid motivation. Topology is super interesting, and topological protection is a very interesting concept. I think it's not yet clear to what extent it works. For example, recently we've published papers where we've shown fractional antiskyrmions at the edges of a lamella which we've created from this Heusler material in which we see the antiskyrmions. So it's not clear then, and these fractional antiskyrmions, this is a collaboration with Daniel Lawson, he's a theorist, a very fantastic theorist at University of Basel, then they've shown that the winding number can be fractional, can be any number, it's not integer. So that suggests that there's less stability or less topological protection than you'd otherwise expect.
Okay, thank you very much for your answer.
Thank you, Akshat. Saugata, please unmute and ask. You want me to read? Or Saugata, can you do that? Okay, I see his chat box. What are the ways to generate ionic currents? Are they somehow related to the orbital currents?
No, ionic currents have nothing to do with orbital currents. Ionic currents are really currents of ions. So for example, we've shown that if you take a thin layer of an oxide material and you cover it with a so-called ionic liquid, you can create very large electric fields at the surface. And we've shown that these will start to either add or remove oxygen. And then by so doing, you can change, let's say, an insulating layer of vanadium dioxide into a metallic layer, or more recently, we've shown if you take a strontium cobalt-03, which is a metallic ferromagnet, you can turn it locally into an insulating antiferromagnet or vice versa. So this is the concept. They're very different from orbital currents. These are physical currents of ions.
Okay, thank you. Ansuman, please unmute and ask.
Am I audible?
Yeah. Yes.
Hello, sir. So I'm currently working on triplet superconductivity for my final year master. So I have two questions. As you were mentioning something on superconducting racetrack. First of all, given the usual singlet to triplet conversion efficiency, which is currently being achieved through devices, is it still sufficient to apply, like is the amount of triplet generated sufficient to apply spin transfer torque into any domain wall and make it move? That was my question one. And second one being, since triplet Cooper pairs are spin polarized, should passing them through a spin orbit material can also generate charge currents through inverse spin Hall effect?
Yeah, they're both very interesting questions. Firstly, yes, this is we don't know the answer to either question, but the first question, in principle, you're right. The super current densities might not be sufficiently large to, let's say, manipulate the materials that I discussed in my talk for current day racetrack, but we can imagine other materials in which they could be big enough. So it's a question of matching the super current density with the material, with the magnetic material. So it's something we're working on. I think is very interesting and exciting, and it's quite frankly never been demonstrated that you can use triplet supercurrents to manipulate magnetization. This is what we want to do. And the second question you asked was about, could we use a triplet supercurrent and convert it into a charge current? And probably one could. So I think this is a very interesting question.
Okay, thank you. Devakant, please unmute and ask.
Yeah, Professor Parkin, very nice talk overview. I have a very general question, because we know this proximity effect is very ubiquitous. I mean, it has been studied in the context of metals. I have considered magnetic material and metals. So now the question is, when you are putting a spin orbit coupled material to a magnetic material, so I just want to know the difference. So what is hindering here, or what is helping here to get magnetic in a spin orbit coupled material as compared to a normal metal?
Okay, so I think of course you're totally right. The concept of proximity-induced magnetization is very general, and you should see it in most systems. And it's just a question of how big it is. So it hasn't really been extensively explored, but of course the systems in which it has been observed is certainly platinum, and you can see it in other systems, right? So I think it's your question is a very good one. Hasn't really been extensively explored, but I believe it to be very important in many different systems. And as you said, it appears to be derived from spin-orbit coupling. So you should see it in many different systems.
No, the point is whether it is assisting, I mean, the induced magnetic effect, is it, I mean, is it more in a spin-orbit coupled system? That is what just I want to get an analogy.
Yeah, it would be more in a spin-orbit coupled system. Is it helpful or unhelpful? That depends on the context.
Okay.
So let's say in our Josephson diode effect, you can read about it in Nature Materials, then we use it, the proximity-induced magnetization, to break time reversal symmetry and enable this Josephson diode effect. So therefore, it's super helpful. Now, in a racetrack device, you could argue it's not so helpful because you're creating additional magnetization, and maybe you have to switch that too.
All right. Thank you very much. A quick question, but the old topic, this spin valve. I could not follow. Why do you want this orthogonal structure spin valve? How the spin transfer?
Yeah, well, okay, very good. Yeah. You want it, let's say, if you have two magnetic moments, let's say, which are parallel, anti-parallel, when you start rotating the magnetization, the resistance will change very little, right? Because the resistance changes from parallel to anti-parallel. They're the two extremes. So when they're orthogonal, then the change in the direction of the magnetization of one will cause a larger change in resistance. It's because the dependence of the resistance has a sinusoidal dependence on the angle. So when they're exactly parallel or anti-parallel, you wiggle them a little bit, there's a small change in signal. The maximum change in signal per unit angular change is when they're orthogonal to one another. That's the reason.
Okay, thank you very much.
Thank you. Surya, one question each. Surya, please, unmute and ask.
So, thank you, Professor Parkin, for your nice, interesting talk. So, this is Dr. Surya Jamalmadka from IIT Hyderabad. So, we basically work on these neuromorphic devices. I just have a query regarding the kind of device that will be helpful for this one, whether the charged based or spin based will be better.
I think people are looking at a lot of different, let's say, Julie Grolier in Paris has done some very nice work on using spin nanotorque oscillators. And you could use oscillators, it's a very common theme in computing to use oscillators to create computing devices. And so you could use spin-based oscillators, or you could use, let's say, in VO2, you can also get vanadium dioxide to oscillate by thermal means. So I think it's very interesting, which type of devices might be the most interesting. But I think this is really, we're in very early stages of understanding neuromorphic computing.
Okay, thank you. Yeah.
Thank you. This please unmute and ask.
Good evening, Dr. Parkin. My question was regarding the racetracks. In in the racetracks, you were suggesting using the ruthenium wafers as a AFM for the AFM coupling. So
Yeah.
there have been some studies of biomagnetic nanoparticles for AFM interface coupling. So they can be useful for making more miniaturized versions of these thin films. So I was wondering, were there any engineering constraints in following up on that?
Not entirely sure what you mean by nanoparticles in this context.
No, they're biomagnetic core or core or shell-based nanoparticles. There was a study regarding this where they showed robust AFM coupling between core and shell in I think iron and manganese oxide-based nanoparticles.
Yeah, so nanoparticles are certainly very interesting. And magnetic nanoparticles, often the surface has a different structure from the interior, and it can be distorted for a whole variety of reasons. Any surface, of course, the exchange of those surface moments is distinct from the interior moments because they have no next nearest neighbor, and this can cause distinct structures at the boundary versus the interior. Typically, the exchange is weaker, so you see stronger temperature dependence. It was shown a long time ago, for example, by Maton and Edwards, that the temperature dependence of the surface of a material, a magnetic layer, is twice, or have twice, roughly speaking, the temperature dependence of the magnetization versus the interior. So magnetic nanoparticles are certainly interesting, and there's a huge amount of work on. You can take a magnetic nanoparticle and you can put certain chemicals on it and then use it to detect or attract certain types of chemicals. But it's a totally different field from, let's say, racetrack memory, and the nature of what they would be used for is very distinct from racetrack memory.
Okay, there are a few questions in the chat box. Maybe I will just take one or two. What is the behavior of magnetoresistance if an antiferromagnetic material layer, metal or insulator, is sandwiched between two ferromagnetic layers? Very interesting question.
Okay, if you have an antiferromagnet between two magnetic layers, then, well, it depends on the antiferromagnet. Typically, I don't know exactly what you mean. Let's say if you have nickel oxide or something like this, then, you can, of course, expect some kind of interaction from one magnetic layer to the other one. So I think it's interesting. I really can't point to any particularly interesting properties, but maybe there are some.
Yeah, well, it can be just dipolar arctic coil couple just on it's a metal or oxide. I don't know. It's very interesting. Well, the last one maybe we can take. There are three types of scormions which are most stable. When two are chosen for a stack, then stability of two different types can be different. How here we deal the.
So it turns out, let's say if you take the original skermions in B20 materials like manganese silicon or iron germanium, there tend to be very limited phase space in temperature and magnetic field where they are stable, and they typically stabilize close to the ordering temperature in magnetic fields. So it turns out the anti-skermion is much more stable, and the reason is that the anti-skermion, you get an anti-skermion in materials with particular symmetries in which the Dzerzhinsky-Maria exchange vector has no component along, let's say, the tetragonal axis of the material, in this case, the Heusler material. And then in plane, it changes depending upon the direction. This is why you get these very complex anti-skermionic structures. And it means that as you go in the third direction, the structure doesn't change. It basically remains the same anti-skermion. You have very stable structures. And this is the reason why probably anti-skermions can be found over a much wider range of temperature and magnetic field than can typically B20 skermionic structures. So this is the advantage of anti-skermions. It's the nature of the Dzerzhinsky-Maria exchange and its dependence on the crystal orientation that makes the anti-skermionic objects more stable, more robust.
Okay, thank you. I think that's about time. Stuart, if you could kindly stop sharing your screen. Don't leave the call.
Okay.
Stop
Stop sharing. Okay,
yes.
I stopped sharing.
All right, I will share my screen. It has been a wonderful interactions. So I would like to present a small memento from our W2S team. I will read it for you. The W2S seminar webinar series on spintronics, National Institute of Science, Education and Research, that's NISER, Bhubaneswar, India. Takes pleasure in presenting this plaque to Professor Dr. Stuart S P Parkin from Max Planck Institute for Microstructure Physics in Halle in Germany, in recognition and appreciation for being a valuable speaker to give a lecture on beyond charge currents, spin and ion currents for future data storage and computing technologies. So with this brief presentation, I like to thank you all. First of all, thank you so much, Stuart, for your very kind time to join and interact. And you see, there's like nearly 300 people listening to your lecture, and still we have nearly 200 people waiting. So listening. So thank you so much, all, and we meet another time. And probably, Stuart, we would invite you to visit NISER next year or so.
Okay.
And if your time permits, please kindly visit us. That would give us a better chance of interacting, particularly with our students and ours. So with that note, I wish you a very nice day, evening ahead, and see you next time. Thank you so much, all. Take care. Bye-bye.
Okay. Thank you very much. Bye-bye.
Bye. Take care, all.